Okay, it's the time. Hello everyone. My name is Ye Nai from China Mobile. I'm very happy to stand here to share our topic, how to run a public cloud on OpenStack. First, let me give you a brief introduction about our public cloud. China Mobile's public cloud is building on OpenStack, and we started this work in early 2015. Until now, we have already building the cloud on more than 8,000 servers, which can provide more than 800,000 virtual CPU. And at the storage level, we can provide more than 20 gigabytes. China Mobile has already been one of the most innovative companies in the world that move fast with OpenStack. In the growing of business, we have faced with many challenges in architecture, high concurrency, and super large scale region. What actually problems have we met today? We will show 3 of them. And I will share the first 2. My partner Yao Fenghua will share the last one. Okay, let's begin. Part 1 is performance enhancement in system disk creation. First, make a background description. How to create a boot volume. Sender will receive the creation request from Lova. Just like this, yeah. And then sender volume load will download the image data from glance to sender volume load. The data is stored in the temporary dictionary. And then we will do the conversion job, convert the data to raw format. And for iSCSI and 5-channel, convert data can write to the backend storage directly. But for Ceph, we should keep the raw image in the sender volume load unless the RBD import is finished. That's all. The last 2 steps will make a big problem when we meet high concurrency. In glance, I/O performance will I/O performance will be one of the bottleneck, and in Cinder, available space for temporary dictionary is also making me headache. Ceph will cost more than double size of image, and the data transmission, that is QM image convert, is also another bottleneck. Although we have volume image cache fraction, but it doesn't work fine in public cloud because the target volume backend may not have cache because one volume type can bind with multiple volume backends by setting the same volume backend name property. Today, I will not explain about volume image cache fraction on the community. You can get more from community. Here, I just focus on how to improve it. First, we redefine a business structure. We make volume image cache in the workflow of glance image upload. You can get the detail from the right picture. Volume type for system disk is set in Cinder configuration file. It's here. We set all the source storage type in the Cinder API load. Whether the image is cached is according to user selection, but public images will be operated by system administrators. It's here. You can select yourself. 3. Cache will be deleted when clearing image. It's here. In this case, both volume will always use colon as long as the image is active. On the other hand, we also provide a rescue mode compatible with our original mode. First, check the image cache. Check the image cache. If exists, just use clone volume to create the bot volume. If otherwise, use the original mode by downloading, converting, and importing. Because of the bottlenecks that said above, we also limited the concurrency. Okay, show some test results. A boot volume of 30 gigabytes image will cost 10 times more when has no cache. Yeah, yes, you can see here. And the smaller image also costs about 3 times more. Okay, this is part 2, performance enhancement in volume backup. First, also introduce the backup ground. This is single backup workflow that picked from Cocker's blog. Yes, you can get address here. The red color words are modified for some mistakes and completion, and the yellow one is note that we will discuss after this. Cinder API receive the request and do the checkmate, update volume status, and create Cinder backup DB, and then RPC cast to Cinder volume load. Cinder backup service, and then we'll call volume driver to attach volume for reading, and then call back backup driver to read data, calculate hash code, compress data, and write the data to the object story. That's all. We have 3 steps to do the enhancement. Step 1, you can specify any backup type as you want. This may not be easy to understand. Let's first look at what the customer wants. This picture shows the most basic requirements. Volume backup on object storage A. When you do restoring, just get it back and start the instance on place A. This is this is just what we can do now by Cinder backup. The data you can restore here in place A. And then, when object storage A is done, we can restore it from another object storage. Here is object storage B. And also start the instance on place A. Restored from here and also in place A. Cinder backup, however, cannot cover it anymore. Even worse, if place A is done, we want recovery business as soon as possible. We want to rebuild it on place B. Existing architecture of Cinder backup does not work. In a word, what the customer wants is just 3 centers in 2 places. But current backup service can just only configure 1 special backup drivers. You can get the detail from this picture. This is just what we want. Block storage A can do a local backup from local backup to object storage A, which can restore fast. And also we want backup the data for a remote on object storage B. When place A is done, we can recover the business as soon as possible. we create a new design concept. This is backup type. Every backup type is binding with one special backup backend storage, just like what we do in volume types. Different from single volume, the backup process is not bind with backend. Every backup process loads the backup driver dynamically. We store the volume data, also the backup type info and the storage info in the object storage. Now is step 2. Use multiple processes to do backup. The community has published this new feature last year. So here I just share some user experience. Single volume is a single process for every backend. Why we need multiple processes for backup? When do backup, we need read the track data, then calculate hash code, and then compress data, and not write volume data, write hash code file, write metadata file to the object storage. Calculation and compression will hold the CPU, so current process will block until the job is finished. This is the main reason. After we use multiple processes, we set it to 5. Yes, just here, this line, yeah. We can get about half usage of bandwidth. This figure is just in our test environment. We have a 16-core server and 10,000 bandwidth. Here is the last step. Incremental backup with Ceph. This is a normal incremental backup. The first backup, we will read the full volume data, calculate hash code for every block. This is the track. This is the track, and every hash code is a block. The second one also need read the full volume data because we need to calculate the hash code as well, and then compare it with parent backup. We will get the diff hash code, and then we will backup this diff data. The third is just the same, and so on. What we made can be divided into 3 categories. First is useless work. It's here. Every time we need read full volume data. The I/O performance in single volume load is headache. Second is busy process. As said above, calculate hash code and compress will cause high CPU usage. Third is poor user experience. We cannot delete any backup in the middle. But the customer doesn't care what it is on the bottom, just want to delete unused backup. Based on the above 3 points, first, we back up a Ceph volume by a new way. When the first backup, we make a snapshot for it, and then do a full backup. If not the first one, just get the snapshot diff data, read them, and back up them to the object storage. This is different from Ceph backup driver. We can back up the data to any other object storage. Only the first time we need to read the full data. Otherwise, just read the diff data. And we also add a new interface in librd in order to have the ability to get diff data. So there is no need to calculate the hash code. And compression is not efficient unless the data is just 0. Bandwidth snapshot diff, so we can just skip it. That's all, which makes the Ceph backup with high efficiency. At last, have a talk about the incremental backup. The implementation is very simple. Compare with some backup, get the keep data, and then update the metadata file and the DB info. The difficulty lies in data filtering and merging. No longer explain here. Okay, my share is finished. Welcome my partner, thanks.
Okay, let me introduce the partner 3. The partner 3 is the performance enhancement in Nova Schedule. In the operation of larger scale public cloud, the schedule performance of Nova Schedule we found is very unsatisfactory, especially in the case of high currency bare metal. The final phenomena is the resource schedule conflicts. First, let me introduce the two schedules which are recommended by community. The two filter is filter scheduler and cache scheduler. The difference between these two scheduler is where host state gets from. Filter scheduler get host states from the database every time, and the cache scheduler only get it from the database just one time when the Nova Scheduler service start. Then it will save this state to the memory, and the later request schedule the destination host based the memory data. Fourth, synchronize the memory data in the database. Cache scheduler will execute a period task. But these two schedulers all have a very serious problem. They all do not occupy resource after select the destination host. All of them use the function that send RPC message to Nova computer to confirm and occupy resource. So it will often lead to scheduler resource conflicts. When it happens, it lays on Nova scheduler retry to schedule the next destination. The retry times we can set in NovaConf. There are two problems here. First, when the conflict times over the retry times, the creation request will fail, even if there is a variable resource in our cloud. Second, every retry scheduler will get the host state from the database. When this is a larger scale cloud, the operation will waste much time. Finally, leads to create the resource after a very long time. So we consider why not set the conform and occupy operation to Nova schedule. So we developed a new filter. Its name is locking scheduler. We add a step after filter scheduler select the destination host. After select the destination host, the request needs to write information in the mem cache to show this resource has been occupied by it. Because the mem cache information is shared by all Nova scheduler in the cloud. So when a resource has been occupied by a request, it will not be occupied by other requests. Since the whole process is done in Nova Scheduler service, so we get the host state from database just one time, and no need to send information to the Nova Computer service. Therefore, the performance of scheduler will get improved. At the locking scheduler, we solved the resource conflict problem. But when the cloud has thousands of nodes, we found the filter process also execute match time. So can we improve the filter performance by reduce the time used to filter host? In existing scheduler logic, Nova scheduler filter all hosts one by one to get available nodes. Then wait these available nodes to get the and select a destination from the highest weight nodes hosts. So we consider, can we maintain a weight value for every host, then order all hosts by the weight, and divide these hosts into several groups by the weight values. So when we filter hosts, we do not filter all host directory. We can filter the host group by group. When select the available hosts from higher weight group, then this request can occupy this resource and update the host weight directly. So it will not filter other hosts in other group. So this function can save much time in filter process. This is optimizations China Mobile has done in Nova Scheduler. At last, let me introduce the plan of China Mobile Public Cloud. As a public cloud created by China Mobile, it will become an important part of China Mobile's 5G+. In the future, we will adopt the N at 31 at X construction mode. Strive to build a resource layout of N core level nodes, 31 provisional nodes, and X cooperative nodes. Okay, above is all of our share. Thank you. If everyone ask some questions.
你好，那个咱们都知道 Memcache 它是你即便做一个集群的话，它对于每个节点来说，它数据不是共享的。你一旦把你的所有的调度数据全都放在Memcache 里的话，有一个节点我们重启就会造成数据的丢失。那这样的问题我们怎么来处理的？
我们其实不是把所有的数据都放在那个，就是那个 Memcache 里面。其实 Memcache 只是作为一个临时的，我去保存一个我占用数据的一个信息。最终我所有的很准确的那些数据，还是依赖于我在 Nova Computer 那边去更新我所有的数据库的。就是我是在前面再加了一道资源的占用信息的去核查这个机制。
也就是有了就从 cache 里去，
对，
没有
的话还是依赖从数据库那边去拿。
好，谢谢。
还有吗？还有吗？好。
You've mentioned that you hit a performance issue when you are using bare metal, and as you are provide public cloud, I think there are many situations that user are actually use virtual machine. And my question is that how many compute nodes that provide virtual machine that you have, and do you have any issue um, when provide this kind of service when doing schedule? And yeah, this is the question. My question. And how many compute node you have in one cluster? I mean, one OpenStack deployment.
We have 2,000 computer nodes in our cloud, in one cloud.
Okay.
对
Yeah.
now.
And do you hit any performance issue when you run this kind of cluster in one deployment when doing schedule? And can you share something about this?
We in virtual 就是 VM we faced some performance in scheduler. For example 就是just I said the concurrency concurrency request.
Okay, conflict you mean?
For example, I request first the Nova scheduler. Nova scheduler will filter all will filter all filters and select the destination.
Mhm.
But it will but it not occupy the resource in Nova scheduler. It will send the message send the information to the Nova computer,
Mhm.
and then the Nova computer will confirm this.
Will claim you mean?
对 yeah. At this time, 就是 before the Nova computer confirm this information, this is a request B. First the Nova scheduler. This is it is probably to select the same host to destination.
Yeah.
So
Same question.
same problem.
Yeah.
Yeah.
Okay. This is just like a resource conflict issue problem. And is there any performance? I mean, issue you hit when you have a large cluster, 2,000 compute node in one deployment. And if you do not have any performance problem, so I think you must have done many improvement. I think, for example, Nova side, because in our cluster we have about 1,000 compute node, not 1,000, currently 500, and we will. Our target is 1,000. We actually hit some performance issue. So.
Can you give an example?
Okay. For example, when we have a lot of requests to create a virtual machine, and it will take a very long time, and maybe it will result error to create the virtual machine.
Do you use the volume image cache?
No, we are not use
your
volume.
local
disk,
local
yeah.
virtual machine.
Yeah, local disk.
它是 local 的机器。
Just curious about this.
Block scheduling or just
scheduling.
Just
I mean,
scheduling, not
yeah.
pulling up the VM, right?
About the scaling challenges that they were having with Nova, particularly the image cache and the scheduler. Like, didn't you just? That's what you were talking about. Scaling challenges with large Nova clusters.
Yeah, you're just using the vanilla OpenStack scheduler, right? I guess that's why you hit the performance issue.
Okay. So, you mean if you use cached?
No. I mean, so for your cluster, right? You just use the original scheduler, right? You're just using the original version of the scheduler from Nova, right?
Yeah.
Yeah, for sure you will hit performance issues, but I think I don't know, because I have a question regarding your weight and sorting stuff, right? So the weight, how do you calculate the weight?
We also weighted these values based CPU, RAM, and
Okay.
or just this this
So is it just per host, or you group a whole bunch of hosts together and calculate one weight, and then you sort across them?
only use the Nova's origin weight.
Oh, okay.
We grouped this all hosts based the weight.
Okay. And then you tend to select the one with higher weight first.
Yeah.
Okay. So once you see something, so you don't have to traverse all the list. You just see, okay, if the first one satisfy your request, you go try to schedule on that host. If it doesn't, you go to the next one, right?
Pardon, 不太了解。
I'm just trying to guess what you guys have done over to that like sorting weight stuff because I'm interested with that one.
我也没听懂，你就用中文吧。
哎，你说的这种。
Okay.
我就说你是那个 weight，就是一个 host 算一个 weight，
对，就是我每个 host 都会给它算一个weight，
每个 host，然后你 sort 一下，
对，
然后 sort 一下之后，你就不用在 filter 的时候不用把所有的 host 走一遍，
对，
你只要走就是从第一个最高的位置走起。
就是我有一个分组，因为我的 weight 不会根据所有的量去算这个 weight，我就会根据一些核心的。我为了防止我有一些量可能是过滤器有些特殊的过滤器没用到，所以我是以一种分组的形式，是用那些就是空闲率最高的先去过滤，优先去过滤，这样就保证我只过滤这些最前面的这些 host，不需要像原来的那套流程。比如我有5000个、6000个节点，需要全部的去过滤一遍。其实这个过滤时间我们现在看来是非常耗时的。分组就是根据那个位置。
It is different because the image may have different size. Yeah.
Depending on the.
The most important is use the image input by current volume could not
是不是根据 request，比如说你这个 request，比如说我想要某一些
will bind